Okay, so from the previous example that we were just working on in the first video, we were working on an M&M activity and trying to find the confidence interval for the proportion of blue M&Ms that are in all bags of M&Ms based off of our small little sample. So if you recall from the information that we did in the previous video, we found that our point estimate was almost 28%. So we're going to use this information to find a confidence interval for the proportion of blue M&Ms. So what we're going to do is we're going to go to Stat in StatCrunch, down to Proportion Stats. We took one sample and we have the summary of all that information. Now, if we had the raw data, like in other words, like a whole column of all of the blue, red, yellow, blue, blue, orange, brown, brown, green, and we had a list of all of the colors here, then we would pick with data. But we simply just have the summary. We already went ahead and counted all of the blue M&Ms. So what we want to do there is we want to select the number of successes. In other words, how many blue M&Ms were successfully counted in the bag, and we counted 15 total blue M&Ms. Total, there was 54 M&Ms in the bag. So 15 out of 54, that's going to give us our point estimate. So that's how StatCrunch will calculate that. Then we're going to calculate what's called the confidence interval for the proportion. And we want, for the first part C, we calculated a 95% confidence interval. Now there are two methods for considering confidence intervals. We're only going to use the first one, which is the standard Wald method. So we'll leave that as is. So that's all we have to do. We're going to go ahead and compute that. And notice over here in the box, all the information that it gives me. It gives me that the sample proportion was 0.277 repeating, and that's exactly what we figured out when we divided 15 divided by 54. That's all it did to calculate that. It gave me the standard error. Now remember, the standard error in this case is going to be considered your the standard error is going to be considered everything that's underneath the square root or your standard deviation inside of your calculation. So if you remember back when we were doing this example, we had a 28%, which is our point estimate. We had our critical z value right here, and then everything underneath this square root is what's called the standard error. So everything in this error right here is where they're getting the 0.0609 number. And that gives us then our lower and our upper limits. Right here, this is our lower and our upper limits, which match exactly what we had in our lecture notes. We had 15.8% all the way up to 39.7%, and that matches. Then we went ahead and we did it again. This time we changed it to 99%. So the only thing we're going to do is we're going to go up here to options, and we're going to change our confidence interval. We're going to change this to 99% instead. And so when we compute that, we would expect this interval to widen out. And there it did. Now we have from 11.6% all the way up to 43.9%. So it looks like we have a little bit of rounding error in that one. Okay, so that's how you would calculate that in StatCrunch. So now we're going to move into the next section, which is estimating a population mean. So we talked about how to estimate the population proportion, P. Now let's talk about how to estimate the population mean. So we're going to take a sample statistic, mean, and use that to infer what the population parameter mean is. So however, we will use our normal standard methods. In order to do that, we need to know the population standard deviation, sigma, for the population mean, which usually we don't know. Let's face it, if we don't know the population mean, why would we have the population standard deviation? Okay, so if we don't have the population standard deviation, we can't calculate z-scores. So we have to come up with what's called a new distribution called the t-distribution in order to solve this. So in other words, if you don't have sigma, then we have to use the t-distribution instead. If you do have sigma, you can go ahead with the z distribution that we normally have done, which we'll do an example of later. So the student's t distribution is very similar to the z distribution, but it's a little more conservative because, again, you're missing that extra information. Anytime you're missing evidence, you have to widen out that interval. So the t-score is found just like the z-score below, except for your standard deviation does not use sigma. It uses your standard deviation from your sample and divides it by the square root of n. So again, your sample size is going to play a part in this. It also follows what we call n-1 degrees of freedom, where x bar is the sample mean and s is the sample standard deviation. Let's describe a little bit more about what degrees of freedom are. Okay? In statistics, the degrees of freedom is the number of values in the final calculation of a statistic that are free to vary. In other words, the number of degrees of freedom can be defined as the minimum number of independent coordinates that can specify the position of the system completely. For example, let's say there are 5 chairs in a room and 5 people walk into that room one at a time. Each of the first 4 people have a choice or a freedom to choose between all of the chair options, meaning they can choose any chair that they want. The last person, however, does not get a choice since there's only 1 chair left. Therefore, they do not have the freedom to choose. Therefore, there are only 4 degrees of freedom since the last person has to pick that last chair in order to make the system work. It is important to note that the interpretation of the t-statistics is exactly the same as that of the z-score. The curves are very similar, but you're going to notice that the standard z distribution has a higher peak and a smaller standard deviation than the n distribution, which has a shorter peak and a wider distribution, or a larger standard deviation. However, as the n increases, look here, this really short one with a wide deviation only has 10 degrees of freedom, meaning their n is small. But as n increases to 20 degrees of freedom, it becomes taller and a smaller deviation. And as n approaches an even bigger number, let's say 30 or more, then the peak becomes closer to the z distribution and the standard deviation gets closer to the z as well. So the similarities that we're seeing for these, for small sample sizes, is, well, we know that they're always going to be symmetrical about the mean. Okay, so no matter what size the n is, they're always going to be symmetrical about this middle point, about the mean here. They're both bell-shaped. And they both center around a z of 0, or wherever that mean is. But the differences are when the sample size is small, okay, the t distribution has what we call thicker tails, which means that the sample standard deviation is getting larger. But as the n starts to increase, you're noticing that that t starts to look more and more like the z distribution. So the goal is to create large sample size so we don't actually have to use the t distribution. We can use z, or assume the t and the z are essentially equivalent. We generally want to stick away from small sample sizes to not create this large flat curve. So let's look at some properties of the t distribution. So we already looked at the picture on the previous page, but here's some properties of that. The t distribution is different for different degrees of freedom. The t distribution is centered around 0 and is symmetric. The area under the curve is still 1, so the area under the curve to the right of 0 and to the left of 0 is both 1/2 of the graph. As t increases or decreases without bound, the graph approaches but never equals 0. The area in the tails of the t distribution is a little greater than the area in the tails of the standard normal z distribution because we're using s as an estimate instead of sigma. Thereby we're introducing a further variability of the t statistic. Now, as the sample size n increases, the density curve of T gets closer to the normal Z density curve. This occurs because as the sample size increases, the values of S get closer to the value of sigma by using the law of large numbers. So let's look at a couple of examples and discuss degrees of freedom before we jump into an actual confidence interval problem. So let's assume we have a sample. It has a size of 21 with a 90% confidence level. That means our alpha is the amount we're willing to risk in making a mistake. In this case is going to be 10%, because those numbers have to add up to 1. So alpha over 2 is going to be 0.10 or 10% divided by 2. So in this case will be 0.05. Our degrees of freedom is going to be 1 less than n. So we're going to have 20 degrees of freedom. Our T value we will find by using the T table, which is actually table 6. So it's the table after the Z table. And if we go to your T table, we can find the critical value. So let me pull up the T table for you here. Now in the table 6, which is the T distribution, the first thing you need to find is your degrees of freedom. This particular example had a degrees of freedom of 20, so we're down here in this row. Then what we do is we go across the top to find the area in this right tail. Remember, this grid right here is broken down to have 2 tails, and we decided earlier that each tail was going to have 5% in each tail. So we're going to go to our n is 20, our area in the tail is 0.05, and where that row in that column meet has a t-score of 1.725. So this is going to be our T critical value that we will be using in all of our formulas. Let's try another one. This time let's say n is only 12 with a 95% confidence, and our alpha is only going to be 5%. It's the amount we're willing to make an error. So the area in each of the tails is going to be half of that, so 0.025. Our degrees of freedom is always going to be 1 less than n, so we'll have 11 degrees of freedom. So let's go ahead and find our t-score again for this one. Again, our degrees of freedom was 11, and the area in each tail was 0.025. So that means our T critical value is going to be 2.201. So I'd like you to try the next two and then come back and let's see if we get the same values. So pause the video now. Okay, did you get the values that I got? I found when I had an n of 40 with a 99% confidence interval, I had an alpha level of significance of 1%. Half of that is 0.005. My degrees of freedom was 39, and when I looked up the t value in the table, I got 2.708. With an n of 81, with an 80% confidence level, I had a 20% risk of making an error, which means I had 10% in each tail. That gave me a degrees of freedom of 80 with a t-score of 1.292. So those are the values that we're going to be using in the following formula. So this is a different formula for confidence intervals of mean. So it's going to look similar to your proportion formulas we learned in the first section, but they are slightly different, being that we're using mean instead. So we have to first make sure that the sample is coming from a simple random sample or a randomized experiment. So if the information didn't come from a random sample, then this might be considered bias. So make sure it's random. Also make sure that the sample size is small enough that it's considered independent. It has to be less than 5% of the total population. Also, we have to make sure that the data comes from a population that is normal, or the sample size has to be large. So if you have a small sample, you have to make sure that the population was normal. That then means the sample is also normal just by default. If we don't know that the population is normal, then you got to make sure your sample is large enough. Well, how large is large enough? Okay, generally speaking, we say n has to be greater than or equal to 30. 30 is usually a good enough number. So our lower and our upper bounds are found by these values. Just like we did with proportions, we have what's called a point estimate, which is going to be your sample mean, that's your x bar, and then everything in the circle is going to be your margin of error. That's how much we'll add and or subtract to find our lower and our upper bounds. So let's go ahead now and do an example using the information that we've already found. The first question says, excuse me, how much time do Americans spend eating or drinking? So suppose a random sample of 1,001 Americans that were aged 15 and up. The mean amount is 1.22 hours per day spent eating and drinking with a standard deviation of 0.65. A histogram of time spent eating is skewed right. So off the bat, we know that this is not considered normal. So we need a large sample size in order to construct a confidence interval. Otherwise, we can't do this. Since there is a skew, the sample n has to be large enough that the distribution of the mean will be approximately normal. And as I stated earlier, we generally want an n that is at least 30. Different books will assume different values, but for the sake of our discussion, we'll assume n has to be at least 30. Now in 2010, there were over 200 million Americans that were in this age group. Explain why this, along with the facts that the data was obtained using a random sample, satisfies the requirements. Well, we first need a simple random sample, and that's one of the requirements that has to be made. The sample has to have been random. Also, we need to make sure that the sample is independent. So is the sample itself less than 5% of the total population? Well, of course it is, because there's 200 million Americans in that age group. So 5% of 200 million people is certainly going to be bigger than our sample size. Our sample size was only 1,000. So we have met both of the requirements. So let's go ahead now and determine and interpret a confidence interval. So let's go ahead and do that with the formulas up above. The formulas that we have up above, I'll rewrite. We have our point estimate, which is our x bar. Then we're going to add and subtract our margin of error. Our margin of error is going to be found by t times your sample standard deviation over square root of n. Again, our point estimate, x bar, was given to us in the original equation. It told us that the mean was 1.22 hours spent eating and drinking per day out of our sample. Then we're going to take that point estimate and we're going to add or subtract what's called our margin of error. Remember, everything in here is your margin of error. So we have to calculate that margin of error. Our t value is going to be found from the t table. In order to use the t table properly, we need a couple of things. We need to find our degrees of freedom, so let's write that over here. We need degrees of freedom. Well, degrees of freedom is always n minus 1. N is 1001, so n minus 1 is 1,000. So we have a degrees of freedom of 1,000. We also need to know the area in the right tail. The area in each tail is going to be alpha over 2. Well, alpha is 0.05. So when I divide that by 2, I get 0.025 in each tail. So we're going to go to the t table and we're going to find a t that is associated with that alpha over 2 at that degrees of freedom. So in my table here, my t distribution table 6, I go to I have the area in the tail is 0.025, which is this column here, and I'm going to follow that all the way down until I get degrees of freedom of 1,000. And that's going to be at the very bottom of the page. Down here, you'll see you have degrees of freedom of 1,000, and my t-value would be 1.962. So my t-value will be 1.962. Then we multiply that by the sample standard deviation, which was given to me in the beginning. It is 0.65 divided by square root of n. In this case, n is 1001. So again, everything in the yellow box is my margin of error. 1.22 is my point estimate. And when I put all of that in my calculator, I'm going to get an interval that starts at a lower bound of 1.18 hours all the way up to 1.26 hours. So in an interpretation, I would state that we are 95% confident that the population mean of hours spent eating and drinking is between 1.18 to 1.26 hours. And now we're going to go ahead and calculate that also in StatCrunch. Okay, so to consider a confidence interval using mean, we're going to go to the same place we went previously, which was stat. But instead of using proportion stats, we're going to use t-stats. Again, we are only considering one sample at this time. And again, we do have the summary. So the first thing it asks me for is the sample mean. And that was given to us in the problem, which was 1.22. Then it asks us for the sample standard deviation, which again was given to us as 0.65. Also, we need to know the sample size. The sample size was 1,001. All right, so we gave all the information from the sample. Now we want to calculate a confidence interval. We want the 95% confidence interval, so by default that's already entered in there. And we're going to go ahead and compute that. So you're going to notice up here it gives us all the information that we've already entered in. It already gave us a sample mean and the degrees of freedom, which was calculated by n-1. The standard error was everything inside of the margin of error except for the t critical value. And then it gave us our lower and our upper limits. And you can see that it matches pretty close. We had 1.18 hours all the way up to 1.26 hours. So you see our lower and upper limits do match. Okay, so let's continue our discussion. This time we're going to select the sample size. Just like we did with proportions, let's try to work backwards. Okay, so let's say we want to calculate the sample size that would be needed in order to estimate a population mean within a specific margin of error. Since we don't know the sample size, since that is what we're trying to find, we have to use the normal distribution because the t-distribution requires that we know degrees of freedom, which clearly we don't know. So the sample size required to estimate the population mean with a given level of confidence is designated by this formula here. So as an example, let's say a doctor wants to estimate the mean serum HDL cholesterol of all 20 to 29-year-old females. How many subjects would he need to estimate in order to be within 2 points of a 99% confidence, assuming that the sample standard deviation was 13.4 from earlier studies? So again, using this formula, we're calculating n. So let me rewrite the formula here. And when we put all of that into our calculator, the first thing we need to find is we need to find the z-score. Remember, the z-scores are found from your table 5, and they're already down here in the corner for you, so you don't have to find them. If we want to be 99% confidence, we need a z-score in each tail. It says already divided by 2, so in each tail our z would be 2.575. So that's the z-score we will need. Then we're going to multiply that by s. S should be given to us, right? S was 13.4. All of that's going to be over your margin of error. In this case, we want to be within 2 points. This is our margin of error. 2 points. Then we're going to multiply all of that by itself, or square it. And when I put that into my calculator, I get an N. We'll need at least 298 subjects in our survey. What if we wanted to redo this time with just a 95% confidence, okay? What do you think is going to happen to the number of people that are needed if we want to reduce our confidence from 99 down to 95? In other words, we want to be less confident. We're willing to make some more error. What do you think is going to happen to our N? Let's find out. Our z-score, according to table 5, for 95% confidence, is 1.96. We only get 173 subjects. So if you guessed lower, you were correct. Okay? So as the confidence, as you get less and less confident, you need less and less subjects. Or vice versa, if you want to increase your confidence, you need more people. So as confidence goes up, you need more and more people to prove that confidence. So let's kind of put this all together now. Okay, we've talked about 2 different types of parameter estimating. We talked about proportions, right? Proportions, we use the proportion p-stats in StatCrunch. Now you have to make sure that it is normal. So NP 1 minus p has to be greater than or equal to 10 in order to conduct this interval testing. So that's the criteria that you would need to do a proportion confidence interval. If we're talking mean, you have to first decide whether you have a normal distribution. Okay? If you have a large sample, if n is greater than 30, then you do have a large enough sample. You can go ahead and compute it with the t-interval. However, if you have a small sample and n is not larger than 30, then your data has to come from a population that is normal. If it doesn't come from a population that is normal, we don't have the methods to solve that. We're not going to go through these methods or the bootstrap methods. We're not going to do that in class, but there are ways to go ahead and do that. But if you know it came from a distribution that was normal, then we could go ahead and use t. So we're only going to be using the t-intervals for those that have large samples or those that are small samples but came from a distribution that was already normal. And those are the 2 methods we'll be talking about. So let's go ahead and do another example to try to put this all together. So for example, how much money do you spend on school supplies every semester? Of course, answers would vary if we were doing this in the classroom, right? So in a random sample of students from this particular class, let's demonstrate and determine the mean amount of money that was spent per person on school supplies per person each semester. Okay, so let me do one example, and if we were in a classroom, we would obviously redo this with real data. But let's say I polled everybody in the class, and on average, I found an average of $337.50 was spent on school supplies every semester. And I calculated the standard deviation to be $170.78. Okay, and of course I use StatCrunch to find that because that's much easier than doing that by hand. So the first thing I would need to do is I would need to verify the requirements have been met. Okay, now my class size was less than 30. So I have a problem. I have a small classroom. Since n was less than 30, we have to assume that the population data is normally distributed. So I'm making this assumption. I don't know that, okay? We're also assuming that our small data, let's say I had an n of 16 in the class, right? Let's say I assume that that n, that 16, is going to be less than 5% of all students. So that has been met, of course, because clearly there are many, many more students than 5% of, the 16 that I started with. Also, I need to determine what my degrees of freedom are. My degrees of freedom is going to be one less than my sample size. So my degrees of freedom are 15. So we know that it's normal, or we're assuming it's normal. We know that the sample is independent. I also know that my sample was random. I randomly selected those students. I've met all my requirements. And of course, I've made some assumptions for the sake of this activity. So let's go ahead together and calculate a 95% confidence interval. A 95% confidence interval, we take our point estimate, we add and subtract our critical value from the t-table, times s divided by square root of n. So our x-bar, we already found up here. We found that on average, from our 16 people in the class, they spend on average $337.50 on school supplies every single semester. Then we're going to go ahead and calculate the t-value. Now the t-value is going to be found from the t-table. We need degrees of freedom of 15, and we need to know the area in each tail. Well, since confidence is 95, that means that we're willing to make a 5% error. So alpha over 2 is going to be 0.025, which is the area in each tail. So we're looking for the t-value associated with that area under the curve at the degrees of freedom of 15. So using the t-table, which is table 6, we go to degrees of freedom of 15, and probability in each area of the tail is 0.025, and you can see that our values are going to be 2.131 for t. So we're going to multiply that by the standard deviation, which we found from StatCrunch earlier, divided by square root of n. And when we put all of that into my calculator, we've got our point estimate plus or minus our margin of error, and we get an overall confidence of $246.52 all the way up to $428.48. So I could state in an interpretation, I could state that we are 95% confident that the true mean of school supplies expenditures is between $246 all the way up to $428. So at this point, I'd like you to pause this. Go ahead and answer the next question, which is basically redoing this with a higher confidence. Now remember, I'm going from 95 up to 99, so I want to be more confident. So remember, what's going to happen to my interval when I become more confident? And make sure that that occurs so you make sure you didn't do anything wrong or made a small error. So go ahead and pause the video and calculate this again. Okay, so let's see how you did. I went ahead and calculated these. The only thing that changed, my point estimate was the same. My standard deviation was the same. My n was the same. The only thing that changed was the t out in front, because that t now has to be at a different alpha. Remember, your alpha now is only 1%. So 1% divided by 2 is 0.005. So we had to find a different t value from the t table. So you're going to notice that your interval did increase, right? It got wider. So when you want to become more confident, we expect our interval to widen out because you're going to be confident you're going to hit that target. So in a sentence, we would state the same thing. We would say we are 99% confident that the true mean of school supply expenses is between $211 to $463. And of course, again, let's do this one more time in StatCrunch. Okay, so let's do this one last example in StatCrunch. So again, we're going to go up to Stat, and we're not doing proportions, we're doing means. So we're going to use the T stats with one sample, and this time we have the summary of it. We don't have the whole list of data, which would be, all 16 people in the class. Now, if we were doing this in class and I listed all of your amounts that you spent on school supplies and I had all 16 pieces of data, I would use with summary instead. That would be with data. I have the summary because we've already done this once. So this is just for an explanation. So the sample mean that I found was on average we spent $337.50 on school supplies. And we had a standard deviation of $170.78. Oops. Try that again. There we go. And our sample size was 16 students in the classroom. So we want to jump on down here and we want to find the confidence interval. The first one was 95% confidence. Let's do that one. And you're going to find that the lower and the upper mean, according to our notes, should have been $246.52. We're a tad bit off there, all the way up to $432 and well, ours on our notes say $428.48. So I guess my question would be, why are we a little bit off here? Okay. Now StatCrunch is going to be a little more accurate than we are. In your T distribution table, excuse me, this table, the table where we're getting our T values, has some slight rounding errors in it. When we used our data in this example, we used a t-score of 2.131, which is what we found from the table. And that's as good as we're going to get when we're using tables. But that value, 2.131, actually has many, many more digits after it that you're not seeing. Now, StatCrunch remembers all those digits, and it uses the full t-value, not that rounded number that we found from the table. So the StatCrunch is going to give you a more accurate interval than we did by hand, because remember, the t-table is only accurate to, 3 decimal places. So that's why you're going to see a little bit of difference in the formula versus StatCrunch. And if we do this one more time, let's go ahead and change this to 99%. If we were to change this to 99%, all we have to do is change this one number. And you're going to see that that lower and that upper limit did widen out even more. And it matches within $5 of what we had.